Today we're going to learn about heating and cooling curves. So find this page in your notes packet and make sure you're looking at the right one. Notice that the graph starts at the 0 on the left and goes up and to the right. What we're doing with this graph is looking at the energy changes that occur as phase changes occur. So we're starting with a substance that is cold, and we are adding heat throughout the entire process. So we are going to call this graph a heating curve. So in the title box, we will call this graph a heating curve. Right next to this title, we're going to add a couple of little notes. One is that this is the heating curve for water. And the second one has to do with what kind of process this is. If we're putting energy in means that this whole graph represents an endothermic process. Remember, endothermic means energy in. We're going to go back down to the bottom of the graph and put in one more little note right underneath that has to do with our endothermic process. Remember, this entire time we are adding energy to this substance via heat. So imagine some water on a hot plate, and throughout this whole process we are not turning the hot plate off. This is going to be very similar to what you did in your lab last week, except this is water and not your mystery substance. Okay, so let's start to look at what happens as we heat up this substance. At the beginning of the graph, down here, notice that we are starting well below 0 degrees C. So what state of matter do we have, remember this is water, when we are below 0 degrees C? I hope we all said solid. Below 0 degrees C, water is a solid. So at the beginning of this process, we have ice. And as we raise the temperature of that ice, what kind of energy are we increasing? I hope you remember from last week that whenever you increase the temperature, you are increasing the kinetic energy. So during this part of the graph, between point A and point B, when the temperature is going up, the kinetic energy is going up. That means our molecules are starting to move faster and they have more energy. This continues until we get to point B. And if you look at the temperature where point B is, you should be able to tell me what we call that temperature. I hope you're thinking melting point. 0 degrees C is the melting point for water. From point B to point C, then, we have a phase change taking place. Melting of the ice occurs between point B and point C. So that means that between point B, and point C, we have two phases of water existing together. We have the ice that is melting and the liquid water that is forming. But notice, between point B and point C, notice what's happening to the temperature. Between B and C, the temperature stays the same. So that means that between B and C, the kinetic energy is not going up. But I told you that when we started this, that we were not turning off the hot plate for the whole time. So if there's still energy going in, it must be doing something else. If it's not being used to raise the kinetic energy, to raise the temperature, the heat energy that we're putting in must be being used to do something else. And that something else is melting the solid. So the heat energy that we are putting in is being converted to potential energy, which is increasing as we are breaking the bonds between the molecules. And remember, when we talk about bonds, we're not talking about actual bonds. We're talking about intermolecular forces that are being overcome. The intermolecular forces hold the molecules side by side, and when you're going to go from a solid to a liquid, you have to overcome those forces to pull the molecules away from each other. We can give the amount of energy needed to cause this change a name, and that is called the heat of fusion. The heat of fusion is the amount of energy required to overcome the intermolecular forces and melt the solid. So, during this time between point B and point C, we are still adding energy through heat. We did not turn the hot plate off, but instead of being used to raise the temperature, that energy is being converted to potential energy, which increases as the bonds, which we really know are intermolecular forces, between the molecules are overcome and the solid melts. Once we have melted all of our solid, then we have all liquid water in our container. And once the solid has changed all to liquid, we notice that again the temperature starts to rise, which again means our kinetic energy is rising. Any spot or any part of the graph where you see the temperature going up, that means the kinetic energy is also going up. And so we heat the water from 0 degrees all the way up to 100 degrees. And then, once we get to 100 degrees, we notice that something else starts to take place. And if 0 degrees was called the melting point, then 100 degrees will be called the boiling point. 100 degrees is the normal boiling point for water. So this is where our liquid water begins to change to a gas. And so the liquid at this point is boiling. So between point D and point E, the liquid is boiling, which means that between point D and point E, we have two phases existing together. We have both liquid water and water vapor, otherwise known as steam. And notice at these points between D and E, again, the temperature is staying the same. Between D and E, the temperature stays at 100 degrees, and so that means that something else must be taking place. We're not turning the hot plate off, so energy is still going in, but just like before, when we melted, now, when it's boiling, we will have the same process taking place. We have the energy that's going in as heat being converted to potential energy, which is increasing as we are breaking bonds. And remember, those bonds are actually intermolecular forces, those forces that hold the molecules side by side. And we can give this amount of energy a name, and we call it the heat of vaporization. The heat of vaporization. And that is the amount of energy that is required to overcome the intermolecular forces and boil the substance. The heat of vaporization is the energy required to overcome the intermolecular forces and vaporize the substance. So now we're up to point E, and again at point E to point F, you can see that our temperature is rising, and so that again means that the kinetic energy is rising. And between point E and point F, we have one phase, and that is the gaseous phase. So, if we recap and look at the whole picture all together, you can see the changes that take place from starting at a solid. We heat the solid and increase the kinetic energy until we get to the melting point. At the melting point, we have the two phases existing together, solid and liquid together, while the solid melts. Although we have not turned off our hot plate, while that phase change is taking place, the temperature stays the same. We stay at the melting point. That's because the energy that's going in from the hot plate is being converted to potential energy as we break bonds. And we say bonds because it's easier, but we know that those are really intermolecular forces. The amount of energy that's required to melt a substance is called the heat of fusion. That's the amount of energy you have to put in to overcome those intermolecular forces and melt the substance. Once the substance is all melted, from point C to point D, you can see our temperature is increasing again. That means our kinetic energy is going up, and the only phase that's present between C and D is the liquid phase. Until we get to the boiling point, which is 100 degrees C for water. At the boiling point, we begin to change over from the liquid phase to the gas phase, so both phases are present together. Between point D and point E, the liquid is boiling. Although our hot plate is still on, our temperature stays the same because the energy that's being put in is being used to break those bonds or to break those intermolecular forces. So it's being converted to potential energy by breaking the intermolecular forces, and the amount of energy that's required to do that is called the heat of vaporization. How much energy do you have to put in to overcome the intermolecular forces and vaporize the substance? Once the substance is all vaporized, we have only the gas phase left, and we can continue to heat that and see our temperature rising and our kinetic energy rising. This is, again, called the heating curve for water, and this whole process from top to bottom is endothermic because throughout the whole process we were putting energy in. Okay, now let's do the other side. We'll start with our title, and notice where the graph begins this time, at the top of the temperature scale. So instead of having a heating curve, this time we have a cooling curve. We're still going to be using water as our substance for this example, and throughout this whole process we will be taking heat out or taking energy out. So this is called an exothermic process instead of an endothermic process. Notice this time we're starting at the top of the temperature scale, well above 100 degrees C. So the phase that we have present for water above 100 degrees is the gas phase. And from point A to point B, we are decreasing the temperature. So that means that we are also decreasing the kinetic energy. So our molecules are getting closer together and they are slowing down until we reach 100 degrees C. And we know that we have a phase change occurring at 100 degrees. And we should know that when we go from a gas to a liquid, that is called condensation. So between point B and point C, our gas is condensing. And so the temperature where that phase change occurs is called the condensation point or the condensing point. Notice that this is the same temperature as our other graph when we did the boiling point, and I'm going to abbreviate there, BP for boiling point. The same temperature as the boiling point. Both occur at 100 degrees, at least for water. It just depends on which direction you're going. Are you making things colder for the condensation point, or are you making things warmer for the boiling point? If you are looking at a graph and being asked to label things on the graph or answer questions about the graph, please note the vocabulary. The word point refers to a specific temperature off the graph. Condensing point means 100 degrees C for water. If you were just asked to label on the graph the process of condensation, that would be somewhere over here, for example, between points B and C. But if you're asked for what is the condensation point, that needs to be a specific temperature from the y-axis in this case. So, what's going on during condensation? We have two phases that are present together during condensation. We have the gas phase and the liquid phase. Both exist together while the phase is changing. And as far as the energy, we know that the temperature is not changing while the phase changes. So that means that if kinetic energy is not changing, potential energy must be changing instead. So during condensation, the potential energy is decreasing because we are forming bonds. And we talked about on the other graph, these are not really bonds, these are intermolecular forces. But since we already talked about it, we are not going to write that down twice. The potential energy is decreasing because the kinetic energy is staying the same. So where is that potential energy going? The potential energy during condensation is actually being released and converted to heat. Now it doesn't seem like it would be because this is a cooling process. So whatever heat is being released by the substance is not going to be noticed by you because you are changing the temperature or you are making things colder. We can, however, give this amount of energy a name, and it is called the heat of condensation. The heat of condensation. And that term describes the amount of energy, and I'm going to abbreviate here, the amount of energy that is released while the gas condenses. The heat of condensation is the amount of energy that is released while the gas condenses. So if we look at what we've done so far, we started above 100 degrees with the gas phase of water. We cooled it down to the condensing point, which is the same temperature as the boiling point. The gas starts to condense, so you have both phases present at the same time. Because the kinetic energy is staying the same, it must be the potential energy that's changing. It is decreasing as bonds are being formed. Remember from first semester, BARF, when bonds are being broken, energy is absorbed. When bonds are being formed, energy is released. So this is the amount of energy that is released during condensation, and we call that amount of energy the heat of condensation. So let's keep going. What comes next? If you look at the phases, we have condensed all of our gas, and at point C, we should just have the liquid phase present. So from point C to point D, we just have the liquid phase. And notice that again, our temperature is decreasing. So that means that from point C to point D, the kinetic energy is decreasing as well. Until we get down to point D. And point D occurs at 0 degrees Celsius. So we know, because this is water, we're going to have another phase change taking place here. And this temperature, 0 degrees Celsius, is called the freezing point. Notice that this is the same temperature as the boiling point from our previous graph. We're just going the other direction. This is the freezing point because we are making things colder. At the freezing point, we have two phases existing together. We have both the solid and the liquid phase. Liquid is being frozen. Solid is being made. And at those places, just like before, we have a phase change taking place. So we'll put freezing from point D to point E. And notice again that our kinetic energy is staying the same. So that means we must be changing our potential energy instead. And we are forming bonds again. So potential energy is decreasing because bonds are being formed. We talked about how that's really intermolecular forces, but bonds is easier to say. During this process, when bonds are being formed and the potential energy is decreasing, again we have that potential energy being released and converted to heat, although whatever heat is produced is not noticeable because of the overall conditions that you're creating to freeze the water. The amount of energy that is released here is called the heat of solidification. That's what you're doing, is making a solid. The heat of solidification is the amount, and I'm abbreviating again, amount of potential energy released while the liquid freezes. The amount of energy released while the liquid freezes is called the heat of solidification. So, for the last part of our graph, we have all of the freezing has taken place. So the phase that we have from point E to point F is just solid. And we can continue to cool that solid as the kinetic energy decreases. So if we recap the whole process, this is a cooling curve. You start with the gas phase, you cool it down, decrease its kinetic energy until you hit the condensation point. That's 100 degrees for water. Between point B and point C, we have both phases existing together because condensation is taking place. As condensation takes place, potential energy decreases. It's released and converted to heat. The amount of energy released is called the heat of condensation. Once that's done, then we have the liquid phase. From point C to point D, the liquid is getting colder. We're decreasing kinetic energy until we get to 0 degrees, which is the freezing point for water. At 0 degrees, we have both phases existing together while the liquid is freezing. While those intermolecular forces are forming, the potential energy that's released is being converted to heat. That amount of energy is called the heat of solidification, the amount of potential energy released while the liquid freezes. Once the freezing is done, we have all solid. From point E to point F, we can continue to cool that solid as the kinetic energy decreases. Hopefully, this is close to what your graph looked like for the lab that we did last week. Next, you're going to look at a different type of graph of how to represent very similar information, the three phases and the phase changes between them, called a phase diagram. After that, you'll learn about vapor pressure, and then you'll review and have your test on Thursday. Good luck!